Welcome to Section 4, Lesson 8. Across the previous 7 lessons, we built every tool for working with single linear equations on the coordinate plane. Today, we extend the same toolkit to two variable linear inequalities y less than 2x minus 1, 3x plus 2y less than or equal to 6, and similar forms. The graph of a linear inequality is no longer a single line but a half-plane, an entire two-dimensional region of the coordinate grid that satisfies the inequality. Today we lock in the 3-step half-plane graphing procedure, draw the boundary line either solid or dashed, decide which half-plane to shade, and apply the test point method to confirm the choice. The half-plane visualization is the foundation for systems of linear inequalities and for the feasible regions of linear programming, both of which appear in later courses. First idea on the board. The graph of a linear inequality in two variables is a half-plane, an entire two-dimensional region of the coordinate plane bounded by the line that corresponds to the equality. The line itself separates the plane into two halves, and the inequality picks out one half as the solution region. Every point in the chosen half plane satisfies the inequality, while every point in the other half does not. Understanding the half-plane structure is the conceptual key that unlocks all of two-variable inequality graphing. Second idea. The boundary line is drawn as solid or dashed depending on the strictness of the inequality. For non-strict inequalities, the symbols less than or equal to and greater than or equal to, the boundary line is drawn solid because the points on the line itself are part of the solution. For strict inequalities, less than and greater than, the boundary line is drawn dashed because the points on the line are not part of the solution. The line style convention is universal in algebra textbooks and standardized tests, and getting it right is one of the small craft moves that separates careful students from careless ones. Third idea, to decide which half-plane to shade, use the test point method. Pick any point not on the boundary line, often the origin 0, 0, if the line does not pass through it. Plug the point's coordinates into the original inequality. If the inequality is satisfied at the test point, shade the half-plane containing that test point. If it is not satisfied, shade the other half-plane. The test point method is mechanical, fast, and reliable, and it removes any guesswork about which side of the line is the correct half. Today we walk through one strict inequality example with a dashed line and one non-strict example with a solid line, illustrating both line style cases and the test point procedure on each. The graph of a linear inequality in two variables is a half-plane, an entire region of the coordinate plane, on one side of the boundary line. The boundary line is the graph of the corresponding equality, and the inequality picks out one of the two half-planes as the solution region. Every point in the solution half-plane satisfies the inequality. Here is the line style rule. Non-strict inequalities less than or equal to and greater than or equal to get a solid boundary line because points on the line itself are part of the solution. Strict inequalities less than and greater than get a dashed boundary line because points on the line are not part of the solution. The line style choice happens before any shading and is determined entirely by the inequality symbol. Step 1 in the workflow. Draw the boundary line. Convert the inequality to an equality by replacing the inequality symbol with an equals sign. Graph the resulting line using any of the methods from the previous lessons, and choose the line style based on the strictness of the original inequality. The boundary line divides the plane into two halves and is the visual reference for the shading step. Step 2. Pick a test point not on the boundary line. The origin 0, 0 is the simplest choice if the line does not pass through it, because plugging 0, 0 into the inequality reduces to a quick numerical check. If the line passes through the origin, pick another simple point like 1, 0 or 0, 1. Step 3. plug the test point's coordinates into the original inequality and check whether the resulting numerical inequality is true or false. If true, shade the half plane containing the test point. The test point is in the solution region. If false, shade the other half plane. The test point is not in the solution region, so the other half is. Optionally verify by testing one more point in the shaded region to confirm the inequality holds there as well. Here is the first worked example. Graph the inequality y greater than 2x minus 1. The boundary line is y equals 2x minus 1. The inequality is strict, so the line is dashed, and the test point method will determine which half plane to shade. Step 1. Draw the boundary line y equals 2x minus 1. The line is in slope-intercept form with slope 2 and y-intercept negative 1. Plot the y-intercept at 0, negative 1. Use the slope 2 to find a second point at 1, 1, and draw a line through the 2 points. Make the line dashed rather than solid because the original inequality is strict, meaning the points on the line are not part of the solution. Step 2. Pick a test point not on the boundary line. The origin 0, 0 is not on the line because plugging in gives 0 equals 2 times 0 minus 1, which equals negative 1, and 0 is not equal to negative 1, so the origin is a valid test point. Step 3. Plug the origin into the original inequality greater than 2x minus 1. Substitute x equals 0 and y equals 0, 0 greater than 2 times 0 minus 1, which equals negative 1. So the inequality reduces to 0 greater than negative 1, which is true. The origin satisfies the inequality, so shade the half plane containing the origin. Step 4. The origin sits above and to the left of the boundary line, in this case, in the upper left half plane relative to the line. Shade that entire half plane to indicate the solution region. Every point in the shaded region satisfies y greater than 2x minus 1, and every point in the unshaded region does not. Step 5. Verify by testing a second point in the shaded region, like negative 2, 5. Plug into the inequality 5 greater than 2 times negative 2 minus 1, which equals negative 5. So 5 greater than negative 5, which is true. The verification confirms the shading. So the graph of y greater than 2x minus 1 is the half plane above the dashed line y equals 2x minus 1, with the boundary line itself excluded. The big lesson from this example is the strict inequality case with a dashed line and the origin as the test point. The 3-step procedure of draw boundary, test, shade works mechanically once the line style and test point are chosen carefully. The dashed line is the visual signal that the boundary points are not solutions, and the shading is the visual answer to the inequality. Practice the procedure on a few examples, and the half-plane graphing becomes automatic for any two-variable linear inequality. Here is the second worked example. Graph the inequality 3x plus 2y less than or equal to 6. The boundary line is 3x plus 2y equals 6. The inequality is non-strict, so the line is solid, and the test point method will pick the correct half plane. Draw the boundary line 3x plus 2y equals 6 in standard form. Use the intercept method from lesson 6. Set y equal to 0, 3x equals 6, so x equals 2. The x-intercept is 2, 0. Set x equal to 0, 2y equals 6, so y equals 3. The y-intercept is 0, 3. Plot both intercepts and draw a solid line through them because the original inequality is non-strict. Step 2. Pick a test point not on the boundary line. The origin 0, 0 is not on the line because plugging in gives 3 times 0 plus 2 times 0 equals 0, and 0 is not equal to 6. So the origin is a valid test point. Step 3. Plug the origin into the original inequality 3x plus 2y less than or equal to 6. Substitute x equals 0 and y equals 0. 3 times 0 plus 2 times 0 equals 0, and 0 less than or equal to 6 is true. The origin satisfies the inequality, so shade the half plane containing the origin. Step 4. The origin sits in the lower left region of the coordinate plane relative to the boundary line which slopes downward from upper left to lower right. The half plane below the line, which contains the origin, is the solution region. Shade the entire half plane below and to the lower left of the solid boundary line. Step 5. Verify by testing a second point in the shaded region like 1, 1. Plug into the inequality 3 times 1 plus 2 times 1 equals 5 and 5 less than or equal to 6 is true. Verification passed. As an additional check, test a point not in the shaded region like 5, 5. Plug in 3 times 5 plus 2 times 5 equals 25 and 25 less than or equal to 6 is false. The inequality fails outside the shaded region as expected. So the graph of 3x plus 2y less than or equal to 6 is the half plane below and to the left of the solid line 3x plus 2y equals 6 with the boundary line included because the inequality is non-strict. The big lesson from this example is the non-strict case with a solid line and the standard form equation graphed by intercepts. The intercept method from lesson 6 is often faster than slope-intercept conversion when the equation is already in standard form, and the solid line is the visual signal that the boundary points are part of the solution. Together with the previous example, you have now seen both line style cases and a clean test point workflow that handles every standard linear inequality on the coordinate plane. 3 mistakes that catch every algebra student during their first weeks of half-plane graphing. Each one is fixable with a small explicit habit applied on every problem. First mistake, choosing the wrong line style for the strictness of the inequality. A student looking at y greater than 2x minus 1 draws a solid line when the strict inequality requires a dashed line. Or vice versa, a student looking at y greater than or equal to 2x minus 1 draws a dashed line when the non-strict inequality requires a solid line. The fix is to memorize the rule cleanly less than or equal to and greater than or equal to get solid lines because the boundary points are solutions, less than and greater than get dashed lines because the boundary points are not solutions. Read the inequality symbol carefully before drawing any line. Second mistake, shading the wrong half plane after correctly identifying the test point status. A student plugs the origin into the inequality, finds the origin satisfies it, and then shades the half plane that does not contain the origin, doing the opposite of what the test result indicates. The rule is shade toward truth if the test point satisfies the inequality, shade the half containing the test point. Repeat the rule out loud while shading until the convention becomes a permanent reflex. Third mistake, skipping the test point step and guessing which half plane to shade by inspection. A student looks at y greater than 2x minus 1 and shades the half above the line by inspection because greater than feels like upward, getting the right answer for the wrong reason. The shortcut works for some inequalities but fails for others, especially when the equation is in standard form rather than slope-intercept form, or when the inequality has subtractions that confuse the spatial intuition. Always do the test point step explicitly. The 15 seconds of testing a point prevents wrong shading on the cases where intuition fails. Half-plane graphing is the foundational visualization tool for 2 variable linear constraints which appear constantly in optimization, machine learning, economics, and game theory across the modern technical world. 4 broad sectors below. In linear programming, an optimization problem with 2 decision variables is visualized as a feasible region on the coordinate plane. The feasible region is the intersection of multiple half-planes, one per linear constraint, and the optimal solution lies at one of the corners of the feasible region. Logistics, scheduling, supply chain management, and many other professional fields use linear programming continuously, and the half-plane visualization is the foundational geometric picture that underlies all of it. Mastering half-plane graphing today is the literal first step into all of operations research. In resource constraint analysis, Real-world problems often have multiple competing limits expressed as inequalities. Time available less than or equal to 40 hours, budget less than or equal to $10,000, capacity less than or equal to 1,000 units, and so on. Each limit becomes a half-plane on the coordinate plane when two of the variables are plotted against each other, and the feasible operating region is the intersection of all the half-planes. Project management, manufacturing planning, and small business operations all rely on this kind of constraint visualization. In machine learning, a linear classifier draws a decision boundary as a line on the feature plane and assigns each data point to one of two classes based on which half-plane the point lies in. The simplest classifier, the perceptron, is exactly a half-plane in the feature space. More sophisticated classifiers like support vector machines extend the half-plane idea to higher dimensional feature spaces, but the foundational geometric picture is the same. The half-plane visualization is the gateway to all of supervised learning. In game theory and strategic analysis, the strategy spaces of two-player games can be partitioned into regions corresponding to different equilibrium outcomes. The boundaries between regions are typically linear inequalities in the strategy parameters, and the resulting partition is a collection of half-planes intersected together. Economists, political scientists, and AI researchers use this kind of strategic visualization to analyze games of conflict and cooperation. The skills you build today scale across all of strategic decision modeling. 3 things to take with you from this lesson today. Half-plane graphing is the visualization tool of two variable linear constraints, and the 3-step procedure from today scales directly into systems of linear inequalities and into the feasible regions of linear programming work in later courses. First, the graph of a linear inequality in two variables is a half-plane and entire two-dimensional region of the coordinate plane on one side of the boundary line. The boundary line is the graph of the corresponding equality, and the inequality picks one of the two halves as the solution. Every point in the chosen half-plane satisfies the inequality, and every point in the other half does not. Understanding the half-plane structure is the conceptual foundation for all two-variable inequality work. Second, use a solid boundary line for non-strict inequalities less than or equal to and greater than or equal to, because the points on the line are part of the solution. Use a dashed boundary line for strict inequalities less than and greater than, because the points on the line are not part of the solution. The line style choice happens before any shading and is determined entirely by the inequality symbol. Read the symbol carefully before drawing. Third, apply the test point method to decide which half-plane to shade. Pick a point not on the boundary line, often the origin 0, 0. Plug the test point into the original inequality and check whether the resulting numerical inequality is true. If true, shade the half-plane containing the test point. If false, shade the other half. Always do the test step explicitly rather than guessing by inspection, because the spatial intuition can fail on standard form equations or on inequalities with negative coefficients. Coming up next, the lesson called Linear Models in Real Life, where the line equation forms from the previous lessons are used to model real-world quantities that change at a constant rate from a known starting point. Linear modeling is the practical payoff of all the Section 4 work and is the bridge between algebra and applied science.